What I would like to do today, before we start on the first subject of the course this semester, is go back and look at some of the topics that you covered on mechanics and materials in the last third of ME 270. And I'd like to do so in the context of one example, and that example being the Northwestern parking garage right across Northwestern from the engineering mall. And what we're going to do here is basically dissect the parking garage and look at the different structural components and remind ourselves of what we know in the stress distribution in those components. The parking garage is really made up of three important components. The first is the structural support beams that you see here. These are the beams that are very visible to you when you look at the front of the garage. The things that provide support for the support beams themselves are the vertical columns. These vertical columns provide support to the support beams through a shoulder, or what's called the corbel. The support beams themselves actually carry the load of what are called the floor beams. And what we see here in this picture is an inside view of the parking garage, the underneath side of the support beams from the floor above, the top side of the the floor beams from the floor that's visible here. So the bottom part of the floor beams, that's what's supporting the cars on this floor. So again, the cars are supported by the floor beams are supported by the support beams, the support beams are supported by the vertical columns. So that's what we see here as we look at the front part of this parking garage. Here, if I peel away the horizontal support beams there on the front from this particular floor, we see the floor beams. These floor beams are beams that are sort of pi, the symbol pi shaped. Again, that's what carries the load of the car. If we look at the free body diagram of the beam from the side view, we see that the horizontal support beams are here. And in terms of forces, there are reaction forces from on the floor beams from the horizontal support beams as this. They're effectively simply supported beams. The support beams themselves, they carry the reactions we just talked about here. In addition to that, they're carrying their own weight. So looking at a free body diagram of the horizontal support beam, we have our reactions over here on the left and right side. And if we make a mathematical cut through the beam, we see that what we expose here are the two resultants here of the bending moment M and the shear force there of V. And what you've seen before is that the bending moment M, that's a resultant of the normal stresses. And the way that these support beams are loaded through weights, the top fibers of those beams are in compression. The lower fibers are in tension. And recall that for the hypotheses that you had on how the stress distributions were in the beams, there's a linear distribution of the normal stress throughout the thickness of the beam. There's also shear stresses there developed. These are the shear stresses that are the resultants of these are as the shear force there of V. And what you might recall is that these are not linear distributions, but more for rectangular cross section. They're parabolic. For the cross section we have here for the horizontal support beams, probably a little bit different than parabolic, but at least they're not a straight line. And the maximum shear stress happens interior rather than on the outer fibers that you see there for the normal stresses there in the beam. Now when we look at the columns themselves, keep in mind it's the columns are what provide support for the horizontal beams. The load is transmitted from the horizontal beams to the columns through these reactions that we see here. The shoulders that are built in, the corbels that are built into the column is what carries that load. So the forces that we show here are the resultants. In order to find the normal stresses that's carried by the column itself, we make a cut through here. And from a very simple equilibrium equation, we can find that internal resultant force there of F. That's just the sum of the reactions acting on it by the horizontal support beams that are provided support through the column. If we're interested in the stress itself, we know that the stress, the average stress in the cross section, is simply that resultant force F divided by the cross-sectional area there of A. Well, there's also other stresses that are developed in the columns. If we look at the corbels, the shoulders that actually provide the support for the horizontal beams, the reaction force goes on the shoulder as this. If we look at a free body diagram of the shoulder, we have the reaction force there of F. There's a bending moment M. There's a shear force there of V. Shear force V that's equal to the reaction force there of F. The bending moment M depends on that distance D from where the resultant force F is applied in the column itself. We're interested in the shear stress itself. The resultant of that shear stress is V. What is the shear stress? Well, if we look at a differential or a stress element there on that cut of area delta A, if we look at the resultant force of delta V, what you might recall is that the shear stress, assuming that D is small, the shear stress is given by delta V divided by delta A as we let that delta A go to 0. So that is what we see there in terms of the shear stress that's developed in the corbel that actually holds up these horizontal support beams. So all three of these components are things that you have covered before. Bending beams and column, the axial loads in the columns, the shear stresses, the direct shear that's developed there in the corbels. Where we're going to be going in this course is going back over that, looking at problems of more complexity than you've looked at before, and also extending our abilities to look at problems that are a bit more complex. As an example here, let's say that we go out on the Sagamore Parkway here in town. This is north of campus. And what you'll find on the other side of the bridge actually is a railroad bridge going across Sagamore Parkway. If you look at the details of this, the railroad bridge is supported by a reaction force here on the left side, a reaction force on the right. But looking at the support there in the middle, we see that the bridge here is actually made up of two beams. So instead of having a single reaction force in the middle, we have two. The point being is that that beam, that support beam there, is actually not one continuous one, but it's actually two. And these are beam reactions that we can easily find. You found them before when you looked at ME 270, no difficulty. However, if you move out Sagamore Parkway, you get on I-65, you head south toward Indianapolis, one of the first overpasses you'll see is the one that's shown here in the figure. Again, it looks like a beam. It's got a support over here on the left side, support on the right. But if you look closely here, that is actually one beam all the way through. Schematically, our beam looks like this. we have three reactions, one on the left, one on the right, and one in the middle. Why is that more complicated? Well, this is what's known as an indeterminate beam. We cannot find the reactions simply by looking at equilibrium. This is going to be a very common occurrence in many structures of interest where you can't find the reactions through equilibrium. You know that's a real problem because that's the first step you go through when you look at a stress analysis in a component is you got to know the reactions. And from the reactions you get the internal resultants. The resultants give you the stress. But that critical first step we can't do. And that's an issue we're going to deal with all semester long in looking at indeterminate structures. Another, driving a little further down I-665, you'll see another overpass very similar to this. It's one span all the way through. You have reactions at the ends, reactions in the middle. This one is a bit longer than the one we had before. Same idea. We're going to have to develop new methods here for doing the analysis when these problems are indeterminate. Another couple issues we're going to cover in this course are covered by what we see in this picture. We see a picture of some railroad rails, which you would like for them to be straight and equal distance apart, but that's not what happened here. What happened is that these rails experience a fairly large temperature increase, and we see that, let's say from here maybe back to down here at the bottom, those rails tried to expand due to the increased heat, and they had nowhere to go. It developed an axial load in the rail itself due to the thermal strains, therefore giving a thermal stress, and the rails buckled. It's not something you've dealt with before back in 270. It's a different sort of issue, a different kind of failure than what you've seen before. Both the thermal strains, thermal stresses, and buckling will be topics that we're going to cover in this course along with some others. So hopefully this review here on some very commonly seen things in your everyday life will help motivate us on understanding why some of the topics we're going to be covering here are quite important and relevant to what we want to learn.